Of all the countless wonders scattered throughout our vast solar system, there are certain places shrouded in a veil of mystery, captivating us precisely because they are so distant and alien. Among these enigmatic worlds, two planets stand out, icy giants hidden at the cold, dim fringes of our solar system. Their bluish hues, turbulent atmospheres, and secretive inner worlds continue to challenge our imagination, inspiring curiosity and exploration. Of course, we are speaking about Uranus and Neptune, the solar system's distant sentinels. It may seem astonishing that these giant worlds were discovered relatively recently. Jupiter and Saturn have been known since ancient times, visible to the naked eye as wandering stars in the night sky, intriguing humanity for millennia. But Uranus was first spotted only in 1781 by the brilliant astronomer William Herschel. Using what by today's standards was a fairly modest telescope, he saw what he initially mistook for a comet. However, careful calculations revealed this object to be orbiting the Sun at a distance far beyond Saturn, making it the first new planet to be discovered in recorded human history. The discovery of Uranus opened a new chapter in astronomy, expanding our cosmic horizons. Yet the discoveries didn't end there. Observations of Uranus's orbit soon revealed unexplained perturbations, as if something even more distant were pulling at it, affecting its path around the Sun. Based on precise mathematical predictions by astronomers Urbain Le Verrier and John Couch Adams, Neptune, an even more distant giant, was discovered in 1846. This marked one of the greatest triumphs in the history of astronomy, a planet found not simply through observation, but through mathematics alone. Both Uranus and Neptune reside in a region far from the warmth of the Sun, at distances of 19.2 and 30 astronomical units respectively. This means sunlight reaching these planets is hundreds of times weaker than on Earth, making their worlds unimaginably cold and dark. Uranus, slightly closer, completes one orbit around the Sun roughly every 84 Earth years, whereas Neptune, further out, takes an astounding 165 years to circle the Sun just once. Despite such differences in orbit, both planets share remarkable similarities, enough so that scientists categorize them as ice giants. The term ice giant highlights their unique composition compared to the gas giants Jupiter and Saturn. Unlike their larger gas siblings, whose thick atmospheres consist primarily of hydrogen and helium, the inner layers of Uranus and Neptune are rich in heavier substances, ices of water, methane, ammonia, and possibly heavier elements. In fact, even though we call them ice giants, deep within their interiors, pressures and temperatures rise so dramatically that water and ammonia behave in ways unimaginable on Earth, forming hot supersonic oceans with temperatures exceeding several thousand degrees Celsius. According to scientists, beneath their dense atmospheres lie extensive layers composed mainly of these exotic, electrically conductive fluids, surrounding rocky Earth-sized cores. The atmospheres of Uranus and Neptune primarily consist of hydrogen and helium, but unlike the gas giants, Jupiter and Saturn, their vibrant blue colors come from significant quantities of methane. Methane in their upper atmospheres absorbs red wavelengths of sunlight, reflecting primarily blue-green shades back into space, giving these distant worlds their strikingly beautiful aquamarine appearance. However, despite their apparent tranquility from afar, their atmospheres are anything but calm. Uranus and Neptune both experience powerful storms, raging winds, and chaotic turbulence, far surpassing anything found on Earth. On Neptune, wind speeds have been measured reaching nearly 2,000 kilometers per hour, more than twice the speed of sound, making them the fastest planetary winds ever recorded in the solar system. It's precisely these contrasts between serene visual appearance and violent climatic phenomena that intrigue astronomers. Interestingly, Uranus presents another peculiar trait that sets it apart from all other planets. It rotates on its side. While most planets have axes slightly tilted, like Earth's moderate 23 degrees, Uranus is tipped over by almost 98 degrees, essentially lying sideways relative to its orbit. Scientists believe a massive collision with another celestial body billions of years ago is responsible for this peculiar orientation, literally knocking the planet off balance. As a result, Uranus experiences extreme seasons. Each pole faces the sun continuously for 21 Earth years at a time, plunging the other hemisphere into a long, freezing darkness. This unusual arrangement leads to prolonged periods of summer and winter, unlike anything experienced on Earth, each lasting decades. Neptune, though more conventionally oriented, also surprises scientists with its fierce atmospheric conditions. Winds on Neptune can reach speeds of up to 2,100 kilometers per hour, making them the fastest recorded in the solar system, roughly 3 times faster than Earth's most violent hurricanes. One of Neptune's most striking features, observed by the Voyager 2 spacecraft in 1989, was the so-called Great Dark Spot, a storm larger than Earth itself. Intriguingly, when the Hubble Space Telescope attempted to observe this storm a few years later, it had mysteriously disappeared, indicating how rapidly weather conditions change in Neptune's turbulent skies. Unlike Earth's hurricanes, fueled by solar heat, Neptune's storms draw their energy from the planet's internal heat source, radiating outwards into the freezing cold vacuum of space. Despite their fascinating atmospheres, both planets also boast intricate ring systems, though far less spectacular and visible compared to Saturn's famed rings. Uranus has 13 known rings, dark and narrow, consisting of particles likely composed of ice mixed with carbon-rich dust, giving them a dark charcoal gray color. Neptune's rings are equally mysterious. They were definitively confirmed only by the Voyager 2 spacecraft flyby in 1989, composed primarily of dust and ice particles, dark, tenuous, and elusive. These rings remain a fascinating mystery for astronomers, hinting at a violent past filled with cosmic collisions and fragmentation events. In addition to rings, both Uranus and Neptune possess numerous moons. Uranus has 27 known satellites, most notably Titania, Oberon, Miranda, Umbriel, and Ariel, each a unique, icy world with a complex geological history of its own. Neptune's moon system, though less numerous, counts among its members Triton, one of the most geologically active moons in the entire solar system. Triton boasts geysers erupting from its frozen surface, ejecting icy particles several kilometers high into its tenuous atmosphere. Scientists suspect that beneath Triton's icy crust, there may exist a subterranean ocean warmed by tidal heating, similar to moons like Europa and Enceladus, raising intriguing possibilities for extraterrestrial microbial life. Since their initial discoveries, Uranus and Neptune have been visited only briefly by a single space probe, Voyager 2, which flew by Uranus in 1986 and Neptune in 1989, sending back the first detailed images and vital data on atmospheric conditions, magnetic fields, rings, and moons. Today, no dedicated missions to these distant worlds have yet been undertaken. However, astronomers worldwide increasingly advocate for ambitious future explorations. Concepts for orbiters and atmospheric probes have been proposed, aiming to unravel the enigmatic ice giants' countless mysteries. From their bizarre magnetic fields, which are inexplicably offset from their rotational axes, to their hidden interior oceans and peculiar chemistry. Studying Uranus and Neptune goes far beyond mere scientific curiosity. These distant worlds hold critical clues about the early formation and evolution of planetary systems. Understanding their composition, history, and formation can shed vital light on the distribution and diversity of exoplanets throughout our galaxy. Moreover, their role in sculpting the outer solar system and possibly influencing life's emergence on Earth is still not fully understood. Every bit of knowledge gleaned from these remote worlds opens doors to comprehending planetary evolution, habitability conditions, and the intricate dynamics shaping our universe. Thus, when we gaze towards Uranus and Neptune, we are reminded of how mysterious and unexplored even our close cosmic neighborhood remains. Each new observation and future mission promises thrilling discoveries, perhaps even rewriting our fundamental understanding of planet formation and evolution. Who knows, perhaps beneath the icy clouds, we might discover secrets that could rewrite our understanding of what constitutes conditions favorable for life. The ice giants hold profound implications not only for planetary science, but also for the eternal human quest to understand our origins and place in the cosmos. With every future mission, we come closer to decoding the stories locked within these distant, silent worlds, waiting patiently at the solar system's edge. For decades, Pluto remained one of the most enigmatic objects on the outer fringes of the solar system. Even after its discovery, when astronomers could barely make out its faint glow against the backdrop of stars, it remained overshadowed by the much larger and more massive giant planets. Only in the late 20th and early 21st centuries, thanks to technological advancements and the growing interest in dwarf worlds, did Pluto step into the limelight. Many of us still remember the controversy surrounding its status. For a long time, it was considered the ninth planet, but in 2006, the International Astronomical Union revised the classification, relegating Pluto to the category of dwarf planets. Despite this formal demotion, this distant world on the edge of the solar system continues to attract the interest of scientists and space enthusiasts. Its icy plains, breathtaking mountains, and thin, ever-changing atmosphere depict an extraordinary world where temperatures drop to exotic extremes and sunlight barely illuminates its desolate landscapes. Today, we embark on a journey through Pluto, reflecting on its history, characteristics, exploration, and why it remains crucial for understanding the evolution of the farthest reaches of the solar system. From a historical perspective, Pluto was discovered relatively late in 1930, thanks to the observations of American astronomer Clyde Tombaugh at Lowell Observatory. At the time, astronomers were searching for Planet X, a hypothesized object believed to influence the orbits of Neptune and Uranus. Although modern understanding of planetary dynamics suggests that Percival Lowell's and others' calculations contained errors, this search program ultimately led to Pluto's discovery. Back then, its planetary status was unquestioned, as no comparable trans-Neptunian objects had yet been found. Over time, as astronomers discovered other bodies in the Kuiper Belt, such as Makemake, Haumea, and later Eris, the question arose, should Pluto still be considered the unique ninth planet, or was it merely one of many icy objects beyond Neptune? In 2006, the IAU introduced a new definition of planet, which Pluto failed to meet, primarily because it had not cleared its orbit. Thus, the category of dwarf planets was established. However, despite this reclassification, Pluto's significance in astronomy did not diminish. On the contrary, the debate over its status fueled further interest, and the New Horizons mission, which we will discuss later, became one of the most impressive expeditions to the outer solar system. In terms of basic characteristics, Pluto is relatively compact. Its diameter is approximately 2,377 kilometers, making it smaller than the Moon, which has a diameter of about 3,474 kilometers. Pluto's mass is around 1.3 times 10 to the 22nd kilograms, which is about 6 times less than the Moon's mass. Its estimated density ranges from 1.85 to 2.0 grams per cubic centimeter, indicating a substantial proportion of rocky material in addition to ice. For comparison, the icy moons of Jupiter and Saturn often have lower densities. Thus, Pluto represents a unique hybrid. Its composition includes water ice, nitrogen, methane, and rocky material. In terms of size, Pluto is comparable to some of the largest moons. Io and Europa are slightly larger, but it closely resembles Neptune's moon Triton in both size and many geological features. This suggests that Pluto is a representative of the Kuiper Belt, an icy body that formed on the outskirts of the solar system, where low temperatures and volatile compounds dominated its early environment. Regarding its internal structure, scientists believe Pluto has a relatively large rocky core, surrounded by layers of water ice and other frozen compounds. Estimates suggest that the core could make up 50 to 70% of Pluto's volume. At extremely low temperatures, below -200 degrees Celsius, ice behaves like rock, but under high pressure and slight warming, deeper ice layers may exist in a semi-molten state. Some models predict that beneath Pluto's crust, a subsurface ocean of water mixed with ammonia could exist, though confirming this hypothesis requires more detailed data. Nonetheless, signs of active geology, such as ice mountains, canyons, and possible cryovolcanoes, suggest that processes resembling those seen on the icy moons of giant planets may also occur on Pluto. Scientists speculate that radioactive decay in the rocky core might generate enough heat to sustain a partially liquid layer beneath the surface. This is particularly intriguing as it challenges the earlier assumption that such a small and distant body should be frozen in absolute stasis. A major breakthrough in Pluto exploration came with NASA's New Horizons mission, launched in January 2006. The probe traveled to Pluto for over 9 years, passing Jupiter and using its gravity for acceleration. By the summer of 2015, New Horizons reached Pluto's vicinity, performing a historic flyby on July 14, 2015. During this brief encounter, the spacecraft collected a wealth of data using its cameras and spectrometers, capturing Pluto and its moon parent in stunning detail, revealing surface contrasts and providing new insights into its atmosphere. For the first time, humanity saw Pluto not as a tiny, blurry dot, but as a complex world featuring a vast nitrogen ice plain, unofficially named Sputnik Planitia, towering ice mountains, and even a hazy blue sky and scattered sunlight. These images and measurements exceeded expectations, showcasing a younger and more dynamic terrain than previously imagined. Examining Pluto's surface, the most striking feature is the bright, heart-shaped region known as Tomball Regio. The left side of this area, called Sputnik Planitia, is a massive plain of frozen nitrogen. This nitrogen ice, mixed with methane and carbon monoxide, appears to flow similarly to glaciers on Earth, smoothing out craters and irregularities. Observations indicate a lack of significant impact craters in this region, suggesting that the surface has been geologically active within the last tens or hundreds of millions of years. Another striking feature is the presence of mountain ranges several kilometers high, composed primarily of water ice, which behaves like solid rock under Pluto's extreme cold. Deep canyons and extensive dark regions near the equator appear to be older terrain covered in a thick crust of water ice and other materials. Although Pluto is, on average, about 5.9 billion kilometers from the Sun, more than 39 astronomical units, it possesses a thin but noticeable atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. Surface pressure is extremely low, only a few microbars, about 100,000 times less than Earth's. However, New Horizons detected a striking blue haze caused by complex hydrocarbons, tholins, forming in the upper atmosphere under ultraviolet sunlight. This atmospheric dust creates a delicate glow, and under certain lighting conditions, it forms blue bands around Pluto's disk. The atmosphere constantly escapes into space and partially freezes as Pluto moves farther from the Sun, sublimating again when the planet approaches perihelion. Some scientists compare this breathing process to seasonal changes on Earth, albeit on a much longer timescale, as Pluto's orbit around the Sun takes 248 years. Why is Pluto so important and unique despite losing its planetary status? First, it offers a window into the history of the Kuiper Belt, a region where temperatures remained extremely low for billions of years, preserving volatile compounds. Pluto and its siblings, such as Makemake, Haumea, and Eris, help scientists understand the early solar system's formation. Secondly, Pluto and its largest moon, Charon, with a diameter of about 1,212 kilometers, nearly half of Pluto's size, form a binary system with a center of mass located outside Pluto itself, an unprecedented case among former planets. Their tidal interactions may influence their internal activity. Lastly, Pluto's surprisingly young surface, ice mountains, and potential cryovolcanism suggest a more dynamic geological history than expected for such a small, distant body. The modern era of Pluto exploration is inseparably linked to the New Horizons space probe. Launched on January 19, 2006, from Cape Canaveral, the spacecraft reached Pluto's system in July 2015, performing a historic flyby at a distance of about 12,500 kilometers from the surface. During those brief hours of its closest approach, the probe collected an enormous amount of data, transmitting it back to Earth over the following months and even years, due to the extremely slow transmission speed caused by Pluto's vast distance. These data sets included high-resolution photographs, topographic information, surface ice spectra, atmospheric profiles, and satellite data, Pluto has 5 known moons. Charon, the largest, followed by the smaller Styx, Nix, Kerberos, and Hydra. One of the most remarkable discoveries from New Horizons was the breathtaking panoramic view of Sputnik Planitia, an unofficial but widely used name, the towering ice mountains several kilometers high, deep canyons on Charon, and the mysterious wavy surface structures. New Horizons effectively completed the first, and likely the only visit to Pluto for many decades. After completing its primary mission to study the dwarf planet, the probe continued its journey into the Kuiper Belt, where in 2019 it performed a flyby of the object Arrokoth, previously known as Ultima Thule. At present, no major space agency has concrete plans for another mission to Pluto. However, space exploration enthusiasts have proposed the idea of an orbital station or even a lander. Given the immense technological and financial challenges involved, such a project could only be realized in the distant future. For now, astronomers continue to collect additional data using telescopes such as Hubble and ground-based observatories equipped with adaptive optics. These observations help track surface changes as Pluto moves along its orbit. Scientists predict that as Pluto drifts farther from the Sun, more nitrogen will freeze onto its ice plains, while a portion of its tenuous atmosphere will settle onto the surface as frost. Looking ahead, if humanity develops more advanced propulsion systems, such as improved nuclear or ion drives, we might one day send a spacecraft capable of entering Pluto's orbit, similar to NASA's Cassini mission to Saturn. Such an orbital station could spend years studying Pluto's geological details, the structure of its potential subsurface ocean, atmospheric dynamics, and interactions with the solar wind at the edge of the solar system. However, for now, these remain ambitious ideas requiring groundbreaking technological advancements and vast financial investments. Despite decades of research, Pluto still holds countless mysteries. Once considered the 9th planet of the solar system, later demoted to a dwarf planet, Pluto remains an essential subject of study. Neither the debate over its classification nor its remoteness and small size diminish its importance. Pluto showcases incredibly young regions on its surface, massive mountains composed of water ice, strange dark terrains, and distinct geological features that may still be evolving. The entire Pluto-Charon system is filled with unusual characteristics. The center of their mutual orbit lies in space between them, and Pluto's 5 moons resemble a chaotic cosmic ballet. Another fascinating aspect is Pluto's ultra-thin atmosphere. Despite being so tenuous that it borders on a vacuum, it still produces twilight effects and a delicate haze. This dynamic breathing of Pluto's nitrogen atmosphere, freezing and sublimating depending on its position in orbit, reveals that even at the outermost reaches of the solar system, seasonal changes can occur. Although these changes unfold on an extremely long timescale, Pluto's orbit takes 248 Earth years to complete. They highlight the contrast of this distant world. Pluto provides a window into the processes occurring beyond Neptune, in a region populated by hundreds or even thousands of other icy bodies. By studying it, we gain key insights into the broader Kuiper Belt, a region that significantly influences the dynamics of the solar system's outermost regions. Furthermore, Pluto is an excellent example of how a body smaller than our moon can retain internal heat and exhibit geological activity, likely due to tidal interactions with Charon and possibly even radioactive decay in its rocky core. If a subsurface ocean does exist beneath Pluto's icy crust, it would be an astonishing discovery. We are already familiar with subsurface oceans on the giant moons of Jupiter and Saturn, but finding one on a small, distant dwarf planet would challenge our expectations about where liquid water can persist in the solar system. Looking toward the future, we can hope that the excitement generated by New Horizons will eventually lead to new missions. Perhaps one day we will develop a spacecraft capable of slowing down near Pluto and entering its orbit for long-term exploration. Such a mission could allow us to monitor how Tombaugh Regio's heart shifts, grows, or shrinks with the seasons, how icy volcanoes slowly erupt frozen materials, and how Pluto's weak magnetic field, if it exists, interacts with the solar wind. Additionally, scientists would love to understand how Charon influences Pluto's tidal forces and internal activity, whether Pluto once had a vast subsurface ocean, and how its thin atmosphere interacts with the surrounding environment. All of these questions deserve attention, as answering them would expand our understanding of how the solar system's outermost planets and dwarf planets behave beyond Neptune's orbit. Despite its small size and vast distance from the Sun, Pluto is a truly unique celestial body. It exhibits striking contrasts, from frozen nitrogen plains to towering water ice mountains, from unpredictable cryovolcanism to seasonal atmospheric changes. Its exploration was made possible by visionary projects like New Horizons and the immense enthusiasm of the scientific community, and the probe's 2015 flyby exceeded all expectations. Although life on Pluto is highly unlikely due to its extreme conditions, temperature, pressure, and lack of sunlight, the planet itself provides invaluable insights into the evolution of icy objects originating from the depths of the Kuiper Belt. Moreover, it offers a new perspective on planetary formation and transformation processes across the solar system. In this sense, Pluto's exploration serves a broader purpose, understanding how different kinds of worlds, large and small, hot and cold, massive and tiny, shape the overall structure of our planetary system. If you have any thoughts on what else Pluto might be hiding, or whether another mission should be sent to explore it, feel free to share in the comments. Public interest is one of the driving forces behind science and technology. Perhaps in the future, inspired by the incredible images and discoveries from New Horizons, we will see an even more ambitious project, such as an orbital station that lingers in the Pluto-Charon system for years, closely tracking seasonal and geological changes occurring billions of kilometers from the Sun. For now, let's appreciate the astonishing world that has already been revealed to us thanks to New Horizons, and remember that the universe is filled with countless discoveries waiting to be made. Stay connected as space exploration continues, offering us new insights into the most distant corners of the solar system. Far beyond the familiar orbits of Jupiter and Saturn, and even beyond the enigmatic ice giants Uranus and Neptune, lies a cold and enigmatic frontier, an immense belt populated by countless icy worlds drifting silently in perpetual darkness. This mysterious region, known as the Kuiper Belt, holds secrets that have fascinated astronomers for decades and continues to captivate our imagination today. The Kuiper Belt is a massive ring-shaped region located beyond the orbit of Neptune, beginning approximately 30 astronomical units, AU, from the Sun, where 1 AU is equal to the distance from the Earth to the Sun, and stretching out to about 55 AU and beyond. For comparison, the orbit of Pluto, which is part of this belt, ranges between 30 and 49 astronomical units. At these tremendous distances, sunlight is only a faint glimmer, more than 1,000 times weaker than what we experience on Earth. Here, temperatures plummet to minus 220 degrees Celsius and lower, and these frozen worlds drift silently through space, occasionally disturbed by distant gravitational interactions. This distant region was named in honor of astronomer Gerard Kuiper, who in 1951 first hypothesized the existence of icy objects beyond Neptune. However, Kuiper himself doubted whether such objects would still exist, believing they would have long since dispersed under gravitational influences. Surprisingly, the first Kuiper Belt object was only discovered in 1992, decades after Kuiper's death, by astronomers David Jewett and Jane Liu. Their observations of a faint object orbiting beyond Neptune opened a new chapter in the study of our solar system and changed our understanding of its formation forever. Since this initial discovery, more than 2,000 Kuiper Belt objects, KBOs, have been identified, with countless others estimated to lurk undetected in the darkness. The belt's population is believed to number in millions, possibly billions, ranging from small icy fragments just a few meters wide to enormous dwarf planets comparable in size to Pluto. Among the known objects, Pluto remains the most famous, reclassified in 2006 from a planet to a dwarf planet, precisely because astronomers realized it was just one of many similar bodies inhabiting the Kuiper Belt. What makes the Kuiper Belt so intriguing is its diversity. Unlike the rocky asteroids found closer to the Sun, these distant worlds are predominantly icy, composed mainly of frozen water, ammonia, methane, and other volatile compounds. Their icy surfaces often have dark, reddish hues due to the chemical reactions triggered by ultraviolet radiation from the sun, which breaks down complex organic molecules. These organic-rich surfaces make Kuiper Belt objects incredibly valuable to scientists studying the earliest history of our solar system. Each icy fragment preserves a frozen snapshot of the primordial nebula that gave birth to the sun and planets, offering us precious insights into our cosmic past. Among the numerous inhabitants of the Kuiper Belt, there are several notable objects that astronomers have studied extensively. One of the largest and most fascinating is Eris, discovered in 2005. Slightly smaller in diameter than Pluto, but significantly denser and more massive. Eris orbits the Sun at an astounding distance of about 68 astronomical units at its farthest point. Its discovery was so significant that it directly prompted astronomers to redefine the concept of planet, ultimately leading to Pluto's reclassification. Another intriguing world is Haumea, a rapidly spinning dwarf planet shaped like an elongated ellipsoid. Haumea rotates so swiftly, completing a full spin approximately every 4 hours, that it has become distinctly flattened. Additionally, Haumea possesses at least 2 moons and even a thin ring system, marking it as a unique celestial object in our solar system. Yet another remarkable object is Makemake, which was discovered shortly after Eris. Its surface reflects sunlight with remarkable brightness, hinting at the presence of fresh, reflective ice layers. Interestingly, astronomers recently found evidence suggesting Makemake might host a thin atmosphere when it passes closer to the Sun, an atmosphere that freezes and collapses onto its surface as it moves further away. The famous Pluto, once considered our 9th planet, is now recognized as the Kuiper Belt's most famous dwarf planet. The groundbreaking mission New Horizons, launched in 2006, finally arrived at Pluto in July 2015 after traveling nearly 5 billion kilometers. It sent back extraordinary high-resolution images, revealing a diverse and active world with mountains made of water ice, vast nitrogen glaciers, complex geology, and even possible signs of subsurface liquid oceans. New Horizons revelations provided humanity's first close-up view of the Kuiper Belt and revealed that even in this frozen realm, geological processes remain dynamic and surprisingly active. Further demonstrating the diversity of this region, the Kuiper Belt also contains peculiar binary systems, pairs of similarly sized icy objects orbiting a common center of gravity. One striking example is Arikot, a unique contact binary visited by New Horizons in 2019. Its shape resembles 2 pancake-like lobes gently fused together, hinting that it formed from the gentle collision and merger of 2 smaller bodies billions of years ago. This intriguing object represents the oldest and most primitive celestial body ever explored, preserving critical clues about planet formation processes. The origin and structure of the Kuiper Belt remain a subject of lively scientific discussion. Astronomers believe that gravitational influences, primarily from Neptune and Jupiter, shape this distant ring of icy objects. Computer models suggest that as the giant planets shifted their orbits early in the solar system's history, countless icy planetesimals were ejected outward into the current Kuiper Belt region. This turbulent era, known as the Late Heavy Bombardment, might also have led to numerous impacts that scarred surfaces of moons and planets closer to the Sun, potentially even delivering water and organic compounds to early Earth. But perhaps the most tantalizing mystery associated with the Kuiper Belt is the elusive Planet 9. Some astronomers hypothesize that an unseen, massive planet, possibly a super-Earth, is orbiting far beyond Neptune, influencing the orbits of several distant Kuiper Belt objects. While direct evidence remains elusive, ongoing observations continue to search for this theoretical world, which would fundamentally alter our understanding of the solar system's layout and evolution. Currently, the exploration of the Kuiper Belt remains limited. However, future missions may include robotic spacecraft equipped with advanced instruments designed for long-term observations, or even landers that could touch down on icy worlds to collect samples directly. Spectroscopic analysis, radar mapping, and detailed imaging are just some of the powerful methods planned for these future explorations. As technology advances, we can expect to discover countless new celestial objects, revealing yet more secrets hidden within this remote frontier. The Kuiper Belt, despite its distant and icy quietness, continues to fascinate humanity because it holds answers to fundamental questions about our own origins and the history of our solar system. By studying these primitive worlds, we look billions of years into the past, exploring the building blocks that created Earth and, potentially, provided the materials necessary for life itself. It reminds us that our solar system is a complex and ever-changing environment filled with phenomena we are only beginning to comprehend. Perhaps somewhere deep within these frozen realms await answers to mysteries we have not yet dared to ask. Every new discovery brings us one step closer to understanding not only the history of our planetary neighborhood, but also the broader cosmic story. Who knows what incredible secrets still lie buried in the shadows of the Kuiper Belt? As we continue to reach out further into space, we are certain of one thing. The universe has many more surprises to reveal, and every new mission holds the promise of discoveries that may forever change our view of our place among the stars. For centuries, astronomers have searched the night sky for celestial objects that might reveal the secrets of the cosmos. Some stars shine brilliantly, dominating constellations with their radiant glow, while others are nearly invisible to the naked eye. Silent wanderers moving through space unnoticed by early stargazers. One such star, a dim, unassuming red dwarf known as Barnard's star, has captured the imagination of scientists and dreamers alike. Despite being one of the closest stars to Earth, Barnard's star remained unknown for most of human history. Its true significance only became apparent in the 20th century when astronomers discovered its astonishing speed across the sky. But the real mystery lies in what orbits it. A world that defies expectations, a frozen, windswept exoplanet that may hold the key to understanding planets around red dwarfs. What makes Barnard's star unique? Could its planet be a hidden sanctuary for life, despite its harsh conditions? And why does this ancient star continue to fascinate scientists more than a century after its discovery? Let's embark on a journey to uncover the mysteries of one of the most enigmatic stars in our cosmic neighborhood. For most of human history, Barnard's star remained invisible to astronomers. Too faint to be seen with the naked eye, it escaped notice until E. Barnard, an American astronomer, identified it in 1916. What he discovered shocked the scientific community. This unremarkable red dwarf was moving across the sky faster than any other known star. Its apparent motion, known as proper motion, is the highest of any star relative to the Sun. Barnard's star shifts by an incredible 10.3 arc-seconds per year, meaning that in just a few centuries, it noticeably changes position against the background of distant stars. This rapid motion suggests that Barnard's star is on a journey, perhaps an ancient traveler from another region of the galaxy, making its way through the cosmic void. At just 5.96 light-years away, Barnard's star is the second closest known star system to Earth, surpassed only by Alpha Centauri. This proximity makes it an ideal candidate for study, especially as astronomers seek to understand the worlds that orbit red dwarf stars. But the true excitement began when scientists turned their attention to what might be hidden within Barnard's system, an exoplanet orbiting this ancient star. For decades, astronomers suspected that Barnard's star might host planets. In the 1960s, astronomer Peter van de Kamp claimed to have detected a massive world orbiting it, but later analysis showed his findings to be incorrect. The mystery of whether Barnard's star had planets remained unsolved until 2018, when a breakthrough occurred. Using precise radial velocity measurements from the Cassini and HARP spectrographs, astronomers detected a subtle wobble in the star's motion. This was the unmistakable signature of an orbiting planet. Named Barnard's star B, this exoplanet is classified as a super-Earth, a rocky world larger than Earth but smaller than Neptune. The planet orbits Barnard's star once every 233 days, placing it at a distance where liquid water is unlikely to exist. Due to the faint light from its red dwarf star, Barnard's star B is a cold and frozen world, with surface temperatures estimated to be around minus 170 degrees Celsius or minus 274 degrees Fahrenheit. If this planet has an atmosphere, it might offer some protection against the extreme cold, But without greenhouse gases, it would be an icy desert, a world of perpetual twilight under the dim glow of its ancient sun. Despite its harsh conditions, Barnard's star B is an exciting discovery. It is one of the closest known exoplanets to Earth, and its existence hints at the possibility of more planets in the system waiting to be found. Could there be other, smaller worlds hidden in its orbit? And if so, could any of them be warm enough to support life? One of the most intriguing aspects of Barnard's star is its age. While our Sun is around 4.6 billion years old, Barnard's star is estimated to be at least 10 billion years old, more than twice the age of our solar system. It formed when the Milky Way was still young, at a time when many of the heavier elements that make up planets and life were scarce. As a red dwarf, Barnard's star has burned through its hydrogen fuel at an incredibly slow rate, allowing it to survive for billions of years. Unlike massive stars that explode as supernovae after only a few million years, red dwarfs can live for trillions of years, meaning Barnard's star will outlive the Sun by an unimaginable time span. Its ancient age raises a fascinating question. If planets existed around Barnard's star for billions of years, could life have had enough time to develop? And if so, what might it look like on a world locked in an eternal winter? At first glance, Barnard's star B seems like an unlikely place for life to exist. With temperatures far below freezing, the planet would appear to be a barren wasteland, locked in an icy grip. However, life has a way of surviving in the most extreme environments. On Earth, microorganisms known as extremophiles thrive in deep-sea hydrothermal vents, under Antarctic ice sheets, and in frozen deserts. If Barnard's star B has geothermal activity, it is possible that subsurface oceans could exist beneath layers of ice, similar to Europa or Enceladus in our own solar system. Another possibility is that the planet has retained an atmosphere rich in carbon dioxide or methane, which could create a greenhouse effect, trapping heat and making conditions slightly more hospitable. While this scenario is purely speculative, it opens the door to intriguing possibilities about the adaptability of life in the universe. Imagine setting foot on the surface of Barnard's star B. The sky above would be a deep red twilight as the dim light of Barnard's star struggles to illuminate the frozen landscape. The sun in the sky would be just 1/100th as bright as our sun, casting an eerie glow across the icy plains. The surface would likely be covered in frozen carbon dioxide or nitrogen ice, sculpted by alien winds. The air, if there is any, would be unbreathable, requiring explorers to wear protective suits. If the planet had active volcanism, geysers of water or methane might occasionally erupt from beneath the ice, creating surreal landscapes reminiscent of the geysers on Saturn's moon Enceladus. Would there be any signs of life deep below, in hidden, warm pockets of liquid water? We may not know for certain until we send probes or more advanced telescopes to uncover the truth. Because of its proximity, Barnard's star is an excellent target for future exploration. Several upcoming telescopes, including the James Webb Space Telescope, will study exoplanets in detail, analyzing their atmospheres for signs of habitability. If Barnard's star B has an atmosphere, these instruments may be able to detect water vapor, methane, or even oxygen, potential biosignatures that could indicate the presence of life. Additionally, projects like Breakthrough Starshot aim to develop tiny laser-powered probes that could travel to nearby star systems, including Barnard's star. These spacecraft, no larger than a microchip, could reach speeds of 20% the speed of light, making it possible to send data back within a few decades. Such missions could provide direct images of Barnard's star B, allowing us to see its surface for the first time and determine whether it is a frozen wasteland or something far more mysterious. Barnard's star is more than just a fast-moving red dwarf. It is a gateway to the unknown. It represents the possibility of planets in ancient systems, the search for life in extreme conditions, and the future of interstellar exploration. Though it is cold, old, and dim, Barnard's star and its lone planet may help answer some of the greatest questions in astronomy. Does life require warmth and sunlight, or can it exist in hidden, frozen worlds? What secrets do ancient stars hold about the early universe? As technology advances, humanity is on the verge of unlocking these mysteries. Perhaps one day explorers from Earth will set foot on the icy plains of Barnard's star B, gazing up at its crimson sky and knowing they have touched a world beyond the sun. The night sky has always fascinated humankind. Since ancient times, our ancestors gazed at the stars, wondering about their nature and whether life might exist beyond our small planet. Over the centuries, as science progressed, we unraveled many cosmic mysteries, yet countless more remain unanswered. Among the closest and most intriguing of these celestial objects is the Alpha Centauri system, a stellar trio that might one day become humanity's first destination beyond the solar system. Despite its proximity of just 4.37 light-years, Alpha Centauri remains an enigmatic and complex system, containing at least 3 known stars and possibly several undiscovered exoplanets. Could any of them harbor life? What secrets do these neighboring suns hold? As our telescopes peer deeper into this stellar system, new findings continue to reshape our understanding of the cosmos. Today, we embark on a journey to uncover the mysteries of Alpha Centauri, exploring its past, present, and future as a potential second home for humanity. The story of Alpha Centauri begins not with modern astronomers, but with ancient stargazers who mapped the heavens without telescopes. Visible only from the southern hemisphere, the 2 brightest stars of Alpha Centauri A and Alpha Centauri B, were observed by indigenous cultures long before European explorers ever set foot in the southern hemisphere. However, it was in 1689 that Jean Richaud, a French Jesuit priest and astronomer, first identified Alpha Centauri as a binary star system. His observations, conducted from Pondicherry, India, paved the way for centuries of research. Later in 1915, the 3rd member of the system, Proxima Centauri, was discovered by the Scottish astronomer Robert Innes, marking a groundbreaking revelation. This was the closest star to the Sun. Since then, Alpha Centauri has been a prime target for astronomical observations. From early optical telescopes to the sophisticated space-based instruments of today, astronomers have sought to understand its composition, its planetary potential, and even the possibility of extraterrestrial life. At first glance, Alpha Centauri appears as a single bright star in the constellation Centaurus. However, it is actually a 3-star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Each of these stars plays a distinct role in shaping the system's dynamics. Alpha Centauri A is a G-type main sequence star, similar to our Sun but slightly larger and more luminous. It shines with a warm yellowish hue with a surface temperature of around 5,800 Kelvin. Its slightly greater mass means it burns its nuclear fuel at a faster rate, but it is expected to remain stable for billions of years. Alpha Centauri B, on the other hand, is a K-type star, slightly cooler and smaller than the Sun. It emits a more orange-colored light and has a lower energy output, making it dimmer than its companion. Despite these differences, both stars orbit each other in a complex elliptical dance, completing a full revolution every 79.9 years. But the most fascinating and mysterious member of the trio is Proxima Centauri, a red dwarf. This small, dim star is often overlooked, yet it is the closest star to Earth beyond our Sun. It lies about 0.21 light-years from the central Alpha Centauri binary and takes hundreds of thousands of years to orbit them. Red dwarfs like Proxima are known for their longevity, burning their hydrogen fuel so slowly that they can live for trillions of years. However, they are also infamous for their violent flares, which can dramatically impact any nearby planets. For decades, astronomers have speculated about the presence of planets orbiting Alpha Centauri. Given the system's proximity, discovering an Earth-like world here would be a monumental breakthrough. It would mean that interstellar travel might one day be within our reach. The first significant breakthrough came in 2016, when scientists confirmed the discovery of Proxima b, an exoplanet orbiting within Proxima Centauri's habitable zone. This planet, roughly 1.3 times the mass of Earth, completes a full orbit around its star every 11.2 days. While this sounds promising, Proxima b's environment is likely harsh due to its parent star's intense stellar flares. If it has an atmosphere or strong magnetic field, it might retain conditions favorable for life. However, more research is needed to determine its true habitability. In recent years, astronomers have hinted at the existence of other planets in the system. Proxima Centauri C, a possible super-Earth or mini-Neptune, was detected in 2020, but its habitability remains doubtful due to its greater distance from the star. Meanwhile, speculation continues about whether Alpha Centauri A or B could harbor planets, perhaps even Earth-like ones, though no definitive evidence has been found. Upcoming space telescopes, such as the James Webb Space Telescope and the European Extremely Large Telescope, are expected to shed more light on this question. If a planet is discovered in the habitable zone of Alpha Centauri A or B, it would be the most promising candidate for interstellar exploration. Let's imagine for a moment that humanity has developed the technology to travel to Alpha Centauri. What would an astronaut see upon arrival? If approaching from the outer edges of the system, Proxima Centauri would be the first landmark. It would appear as a dim, reddish dot, barely illuminating its surroundings. As our spacecraft moves closer to Alpha Centauri A and B, the view would become spectacular. These twin stars shine brightly, dominating the sky. If there were habitable planets orbiting them, they would experience an unusual celestial display. Two suns casting golden and orange glows over alien landscapes. If one of these planets harbored life, what might it look like? Would it resemble Earth, with vast oceans and green continents? Or would it be an entirely different world, shaped by an environment unlike anything we know? The answers to these questions remain unknown, but with advancing space technology, we might not have to wait long to find out. Alpha Centauri has long been a subject of fascination in science fiction, from books and movies to video games. But beyond fiction, serious efforts are underway to make interstellar exploration a reality. One of the most ambitious projects is Breakthrough Starshot, an initiative aiming to send small, laser-powered probes to the Alpha Centauri system within the next few decades. Using ultra-thin, light-propelled sails, these miniature spacecraft could travel at 20% of the speed of light, reaching the system in about 20 years. If successful, this mission would mark the first human-made objects to travel beyond the solar system at such high speeds. The data collected could revolutionize our understanding of planetary systems beyond our own. Moreover, with advancements in AI, quantum computing, and autonomous spacecraft, humanity may one day send larger crewed missions to Alpha Centauri. The biggest challenges, radiation exposure, propulsion technology, and self-sustaining habitats, remain unsolved. But given enough time, these obstacles may be overcome. Understanding Alpha Centauri is not just about satisfying scientific curiosity. It is a necessary step in humanity's long-term survival. Our sun, though stable, will eventually exhaust its nuclear fuel, forcing us to look outward for new homes. Interstellar travel may seem like a distant dream, but every breakthrough in astronomy, physics, and engineering brings us closer to making it a reality. Furthermore, the search for exoplanets in Alpha Centauri may help us answer one of the most profound questions. Are we alone in the universe? If life can arise elsewhere, Alpha Centauri is one of the best places to look for it. Even if we do not find extraterrestrial civilizations, the study of planets in this system will teach us about planetary formation, habitability, and the delicate balance that makes Earth so special. Alpha Centauri stands as a beacon of exploration, an emblem of our cosmic curiosity and ambition. It is a system rich with mysteries, 3 stars, potentially habitable planets, and the closest stepping stone to the rest of the galaxy. While reaching it remains a formidable challenge, the first steps are already being taken. Perhaps one day, long after our first pioneers set foot on Mars, a new generation of explorers will embark on the greatest journey of all, an interstellar voyage to Alpha Centauri. Whether as scientists, dreamers, or future travelers among the stars, humanity's connection to its nearest stellar neighbor will only deepen with time. The universe is vast, and Alpha Centauri is but the first step. What awaits beyond? Only time will tell.